Hello, everyone. Welcome to another binary episode of the Day Zero podcast. I'm Spectre, with me is Z. Today we have a bit of discussion on PS5 exploitation, some scoreboard hardware hacking, and a few other topics scattered in there. Before any of that, though, as always, we'll get into the Spot the Vuln solution, of which there was actually two for this week. So I'll let Z get into that. Z, I think you might be muted. Just so you know, I don't hear you
Thank
coming through
you.
at least. On my end.
Yes, I
Okay.
was still muted as I tried talking there. Yeah, kind of two main solutions on this one, maybe three. Well, I'll cover the main thing here. I've got a validate cookie function. This is actually inspired from a WordPress vulnerability. In fairness, this is a 2007 WordPress, not like a modern WordPress bug. Modern WordPress has done a fair amount when it comes to their security. Although still some questionable practices. I won't get into that. The issue here, you'll see that pulls out actually on line 2, it's pulling out just username, expiration time, and an HMAC out of a cookie, so that is completely controllable by an attacker. Checks the time and then calculates a secret, and it calculates what the hash should be using that secret. In an actual code base, the core vulnerability here might not be so obvious when you don't have the secret right next to the computed. See, that's kind of doing the same thing in both. But yeah, you've got the secret being computed without any actual secret information. And then it computes what the proper hash is. So the core idea here, what you should probably be looking for are just like, is the secret actually secret? In this case, it's filled in with completely user-controlled information, so anybody could craft their own valid cookie there. Another thing that was called out, which was kind of an unintended solution, is the usage of double equals. In PHP, you should be using hash equals, which is their secure hash comparison. That would be your ideal way to actually check this. Or at the very least, triple equals, so you don't get any kind of magic hash sort of situation here. It would be a difficult attack to pull off. I'm not even sure if it would actually be possible, but it's I guess a theoretical attack here that you could generate some magic hash. And if you're not familiar with a magic hash attack, that's just because with PHP double equals, it's going to do the type juggling. So it's going to try and convert the types into something that it can actually compare. And if a hash string starts with 0e, it's going to treat that as scientific notation. Actually, I think it will do that with any number and then a lowercase e. I don't think it needs to be lowercase, but then an e and whatever, because it's doing like the exponent for scientific notation. So if you can get a hash, usually this attack is done by using a 0, but you get a hash that starts with that 0e, and then this computation kind of starts to break because instead of thinking it's comparing a couple strings, it's comparing now a number. That said, because of how this hash is generated, I think you might have a really hard time finding something that works, where you can have like the HMAC maybe have that computed be off or whatever. I don't know, because of the interrelationship between that secret and like the hash is generated, it feels like you're going to have a challenge actually calculating it, and of course being SHA-256, a lot more difficult to get that sort of collision compared with like MD5. But it is valid to point out, at the very least, like it is a bad practice. It is a good thing to notice.
One of those things you would write down on a audit or something for sure. But yeah, like fairly simple intended solution there, or the first intended solution anyway. It was almost a little too simple because I was laughing with Z. I actually looked at this quickly when he put it up, and my mind was in C mode still. So I was like, "Why are you accessing the expiration field on the username object?" And in fairness to myself, I haven't written PHP in probably like at least 4 or 5 years. So
Yeah,
it's
that is one of the oddities with PHP. I mean, Perl does this too, and PHP started off as a Perl thing, using the dot as string concatenation rather than like a field access.
yeah. But the fact, like the problem here is just the fact that the secret can be known. So yeah, cool challenge. All right, so up first, we'll talk about some PS5 stuff. I won't really go into the vulnerability or anything like that because I've brought it up before.
Do you recall what
It was
episode
the
that
flows
was?
issue. That we talked about it.
Yeah. I'll pull it up if you don't know offhand. You can keep going.
Yeah, honestly, I don't remember exactly,
All
but
right.
yeah, it was an IPv6 use after free. Part of the reason I wanted to bring it up a bit on the podcast is just because the exploitation environment on the PS5 is pretty interesting. The mitigations that you face there are not really present on most other targets. I mean, PS5 and Xbox, I guess, for the most part, the consoles are pretty standard when it comes to the mitigations and what's being done because AMD does that work for both Microsoft and Sony. But yeah, the big one here is things like execute only memory. And I don't think we've really talked about that on the podcast before. The idea of execute only memory is the fact that you you can't read code pages essentially. Code pages, they can be executed by the CPU, but as soon as you try to do a read access on them, it will throw an exception. Which obviously makes things like reverse engineering really damn difficult, because unless you can bypass that exam somehow, then you're just not going to be able to get the text. You can get the data segments, which could be helpful. You could maybe reverse some of the structures there, which we have done. But yeah, you're pretty limited on what you can do there, and you're very blind.
Yeah, like
That
as I
also obviously
understand,
prohibits ROP too, so you're also limited in your primitives. Go ahead, Z.
yeah, as I understand right now, that's kind of where you're at with the PS5 exploit, correct? Is you kind of had to do some reverse engineering of just the data section. You're kind of blind as to what this data is, because you can't actually see the code that would be using it. And
Yeah,
you know it is definitely unique to the consoles, and the consoles are really one of the few places where XOM makes sense. Because generally speaking, like on your random binary, XOM is just going to or it's not going to do much because you have the binary itself. So who cares? But consoles definitely take some work there. They do hide like their updates. I'm going to assume they're encrypted. Maybe they are only signed.
oh
But
yeah, they're encrypted. There's multiple
yeah,
layers of encryption actually.
yeah, I would assume so because I assume they're also using like the root of trust to store those keys and then keeping you from actually even getting the keys. Anyway, point being, like you don't even have the binary to pull gadgets from, whereas on like a desktop machine, most of the things you're running or even on a server, you've got binaries that you're able to track from somewhere. And that's going to give you the gadgets you need. So it really, this is one of the key areas where XOM as a mitigation really makes sense.
Yeah, another thing that's worth mentioning is if you had XOM on PC, just because of how much more access you have, you would probably be able to disable it pretty easily anyway. So yeah, console environment is one of those areas that makes sense. Another area it would make a lot of sense is IoT. Generally, IoT manufacturers do try reasonably hard to do like obfuscation and prevent people from being able to dump the ROM of the device or whatever. So it would be interesting to see if execute only memory makes its way over there. Um, but yeah, like I said, it limits your primitives because you're not going to be able to ROP unless you really hate life and try to brute force, like do blind ROP basically, like try to brute force the gadgets somehow, like side channeling, or I don't
Yeah,
even
I
know how you
mean,
do it exactly.
since you mentioned blind ROP, like there was the BROP paper, blind ROP paper, but even that, that depended on if I maybe my memory's mistaken here, but I believe the attack itself was like you still need a read gadget to dump the whole memory space and it'll like find its gadgets that way. Maybe I'm wrong. Maybe it did do some brute force there or had an option for it, but I believe it still needed to dump memory. Yeah, brute forcing gadgets does seem pretty painful.
Yeah, I think the only way you could feasibly do it is because you can, and I'm talking about kernel context here, and something like userland, this would be even more difficult. But in kernel, because you have so many pointers in the data segment, including function pointers, you could maybe take like a similar kernel that you can build from FreeBSD or maybe like PS4 kernel in this case. Try to find some gadget that exists in a function, and then find a function pointer to that, and then brute force that way. So like try to find a general area of a gadget and narrow it down.
And
But
I
even that
guess
would not be fun.
I guess with a lot of function pointers being around, like you can try and go the route of whole function gadgets too. Um, that at least feels like it might be a feasible route. Of course, whole function gadgets are a bit of a pain of their own because they generally don't give you just a nice, like, read write this register sort of primitive.
Yeah, which brings me to another mitigation that's on the PS5, which is CFI, which I thought would be kind of cool to talk about because we just talked about CET last week, and so yeah, the kernel in PS5 has Clang-based CFI. What's notable about that is Clang-based CFI is fine-grained. So last week we were talking about those CET bypasses, which involved doing like co-op. So basically using function calls to try to do some useful things like function level gadgets, like what Z was just talking about.
Well,
Um,
virtual functions, like the C++ virtual
yeah,
function does add a little bit of a nicer layer because you're dealing with object fields, relative access. You can do things there that make it a little bit nicer, but yeah.
yeah. But in this case, CFI is enforced. So even though you can read and write to kernel data with an arbitrary read write, if you smash those function pointers, it's not like you can really do something useful with that. So yeah, it's kind of an interesting environment. Unlike PS4, SMAP and SMAP is also enabled, but that's nothing special. That's been on desktop and server for years now. PS4 was just really behind in that respect. We got kind of lucky that that was not there. Although it was in development like 2010 to 2011 or whatever, so SMAP was still pretty fresh at that time. But yeah, it's just kind of an interesting exploit environment. And we've talked about like bypasses for things like CFI and whatever, and we've talked about DOP a lot before, but I don't think we've seen like data oriented programming. For those who don't know what I mean by DOP, I don't think we've really seen it in action too much, but it is in full force here because it's basically all we have at the moment until there's like some way to bypass the hypervisor or whatever. So yeah, I figured I'd talk about it a little bit and bring it up. If you want to check out the exploit, it is on the GitHub there, and it just goes to show the thing I've talked about before, which is the fact that code execution, in my opinion, is overrated. I know it is kind of the like pinnacle of what everyone who writes exploits tries to go for, which it makes sense. It's fancy and it lets you do a lot of stuff, but you don't absolutely need it to do something useful or cool. And this is kind of an example of that because this is just arbitrary read write. There's no code exec, but it's still able to do some patches. And it's allowed us to get a foot in the door to do some additional research, right? So, which is the main goal of what this exploit is. So yeah, I figured I'd talk about it a little bit. It is an interesting environment, and it could be something I see coming to spaces like IoT in the future. A lot of like Z was saying, a lot of different areas. Execute only memory doesn't really make sense. You're gonna have the source code, or you're gonna have the binary unencrypted. So yeah, but in IoT, I could definitely see this kind of environment going over there, and it
IoT is
would
a
be very
really good
useful.
shout. I hadn't thought about that, but yeah, it is. I could definitely see if there. I mean, IoT is also the place where security goes to die at times, or um, it has a very bad reputation. So whether or not they'll start adopting XOM remains to be seen. But there are some devices in the IoT world that are trying to be secure and do make an effort there. Yeah, it would make sense to use XOM there. I could see it being rather impactful in that case.
Yeah, it could
Uh,
make IoT security a little bit stronger and not as much of a meme as it is today.
yeah, assuming it's well implemented. Was it FreeBSD, OpenBSD? I think it was one of the BSDs that had at one point a bug in their implementation for XOM. Where basically like XOM meant that it was always writable or something. It like completely ruined SMAP or SMAP when they had
Uh
XOM enabled because like the flags weren't set how they'd expect. Oh yeah, because it wasn't readable or whatever. Because the flag wasn't set. Oh no,
yeah,
I
I wish
have
I
a
remember what you were talking about because it's ringing a bell. We did have a topic around this, I think. I just can't seem to recall it and can't find it either in my notes. So
yeah. And speaking about that, I the last time we talked about the PlayStation vulnerability, I believe was episode 146. where we talked about I think this is the same vulnerability, remote kernel heap overflow, PPOE driver. Does that sound right?
Oh no, that
Oh,
was
it's a
different.
different one. My bad.
Yeah,
I'm
yeah.
trying to dig it up here because the one you exploit was the one that there's a regression on, right?
Yeah, so it was an IPv6. It was in IPv6 packet options. So there was basically like a race UAF. They weren't doing synchronization properly. You could end up getting two sockets to point to the same packet ops, and that's where you start your memory corruption primitives. Um, Pretty cool bug, but yeah, it was a couple years old, and Sony had a massive regression on that because Flow reported that bug before the PS5 was even like publicly revealed. So yeah,
And
they
yeah,
messed that up.
there it goes. Yeah, there it appears again. Yeah,
Yeah.
unfortunately, I'm not sure what episode we did cover that on. I'll see if I can find the link by the time we put the notes up, but yeah, it's not coming up here for me.
Yeah, I'm not even totally sure if we did cover it because it might have been at a weird time where we were on break, possibly.
Well, I thought
I'm
we
not
covered
100%
it
certain though.
when the regression happened or talked about the regression.
Oh yeah, we talked about that a couple weeks ago. It was either last episode or the episode before that. But it was we just briefly mentioned it. But
Okay.
yeah, I mean, I wanted to shout it out because exploitation wise, it is kind of cool. It's kind of a unique environment. PS5 is a hell of a lot more interesting from an exploitation perspective than the PS4 was. The PS4 was very lax on its security mitigations. They didn't even have ASLR enabled until like 2.50 or something. Like their earlier firmwares didn't even have ASLR in the kernel. So yeah, but the PS5 is a lot stronger. It will take a lot more work, but that's also what makes it a bit more fun to exploit. Um, and
Yeah, I
yeah, I
mean,
mean
it also
it
sounds a little bit more frustrating with XOM, but I mean, it's an interesting challenge. While,
it's definitely more frustrating.
yeah, I mean, it seems like a interesting area though, just because it is a new and novel challenge to start tackling. Like I said, also having CFG going on in there, CFI, just
Yeah,
the extra hurdles to kind of talk a little bit about.
yeah, and it's cool because it collates a lot of mitigations we've talked about on the podcast, but we don't necessarily see very often in the targets that we cover. So yeah, it kind of brings things together a little bit.
Oh,
But
so
yeah,
I guess yeah, we did talk about it just last episode, last
yeah,
binary episode,
okay,
just briefly, but it was there on episode 154.
yeah. And the Hacker One report you can find there. We'll also link it on this episode too if anyone's interested in that, or you could just look at the repo. I put it at the top of the repo. So yeah. All right. So moving on from some PlayStation stuff. Up next, we have a vulnerability reported by Talos in uClibC, which is a lightweight glibc replacement. And I'll let Z get into this one.
And this is a fun issue, I guess. Another place I'd use that fun word. Um, you've got uClibC, which are probably that's I would assume the original is probably like a mu character usually gets replaced with the U. Micro libc, I think. Either way, lightweight libc meant to be used in like situations where you want a lightweight libc. So possibly IoT, they call out here this vulnerability as in Inker UFI home base. Either way, core vulnerability here just has to do with it creating threads, and the process it has for that is it basically starts off at whatever address just has a constant there for thread stack start address. Every thread you create, it just allocates a stack size. Defaults 2 megabytes, kind of takes that address, allocates decrements it 2 megabytes, kind of allocates its spot there as like, here's where your stack's going to be. Don't grow beyond it, which in fairness with threads, that's usually how it works. You don't want to grow too large, or you usually do have that sort of capacity, so that's not too odd. What's a little bit interesting here, though, is as it's creating the stack spaces, every time it's creating the new thread, it's calling mmap. Specifically, it's calling mmap with the map fixed flag, which kind of introduces what I think is the kind of fun bug here, where if you try and mmap an address with the map fixed flag, it will, like, if that address is already allocated to something else, it's just going to eject it and put in this new memory for you. So what can happen is as as it's not really checking for it to be overlapping with any existing memory, like a library being mapped into memory. As you keep going, as it keeps moving the stack further along in memory, it can just end up overwriting libraries that got mapped to the same address, allowing you to overwrite code with stack data. And potentially getting an exploit off that, which is a kind of fun primitive to have. Seems pretty powerful, depending on what control you have over the stack, but and they don't really go into the exploitation here at all. Just the fact that like that issue exists, which I thought was kind of a fun thing to go about. And just before the stream, Spectre and I were kind of talking about how you'd really go about fixing this, because we don't have, or we weren't able to find a patch for it. I didn't look, but Spectre was looking for the patch.
Yeah,
My
so
thought.
you
Go ahead.
uClibC-ng does link to their Git. So I was using the versions they had in the post and trying to see if I could find a patch, but I couldn't find anything. So I don't know. It is something a little bit weird because it seems like it could be like a bit of a dependency issue. So it might have just been they updated the dependency, which fair enough. Because they talk about how Linux threads old is where this vulnerable code is implemented, which is also referred to as the stable version. So there's kind of these two different versions of Linux threads. Though uClibC-ng will only have the one, so it seems like all versions that build root that use ng will have that vulnerable implementation, which they talk about towards the end. But yeah, I couldn't really find the bug, unfortunately. I feel like the way you would fix this, without like obviously an architectural overhaul, which is an option, is just to limit the amount of threads you can create so that you can't bleed your mapping into like library mappings.
So
That
they
said,
do
that also
have
doesn't seem like
that.
a solid fix. So
Kind of. They do have that. They do have thread max, which is the limit to how many threads they can even create. So they do have a maximum. And that is kind of a limitation on it, which is why this probably like on a 64-bit, like you are limited. You can't just go forever. So in a 64-bit system, might be a little bit harder versus like a 32-bit system where, um, things are going to be closer together. So worth at least calling out. They do have a limitation there. And you would just need to set that even smaller, but it doesn't do any checking to ensure it, to make sure like this is how much space it has before a library or anything. It just takes the fixed address and goes with it. And so even that'll limit like your range, but it doesn't really fix the issue. And I think the only way of really fixing it is, more of an architectural thing. Perhaps allocating large regions and then, just implementing your own allocator over it to create the stack space, rather than needing it, like forcing the mapping in there. Having smaller regions so you can, like kind of doing arenas. That idea where you've got off the heap, creating arenas for them. I think another way where you can kind of limit where they are and allocate a new arena as you need it. Yeah, I mean, most of the ways of fixing this, I feel like they're going to be fairly architectural and kind of heavy changes. But it's a fun bug. Like, I'm not sure I've really seen the fix flag used all that often, and then also having it used in a dangerous way, but definitely something to be aware of.
yeah, generally using the fixed flag is not a good idea. And this is one of those problems where it comes down to not fully grasping the implications of the flags you're using and not paying attention to the kernel documentation. Because something like map fix is just super easy to misuse and easy to overlook the implications of what happens when you run into those edge cases, like trying to map over an existing mapping. So yeah, it's kind of an interesting and unique problem because most code isn't going to be M mapping at all, and if they are, they're not going to be doing fixed mappings. It's only something like libc where you would encounter these types of issues. So yeah, I mean, it's not every day you see a CVE with thread allocation can cause mem corruption. That's only something you're going to find in libc. So yeah, bit of a unique issue in that respect. But like you were saying, there is a little bit of a limitation there where it's probably not as practical or not practical at all on 64-bit. But in something like IoT, which is what they're talking about here, they're talking about this in the context of Eufy Homebase. a little bit more of a concern in that area. So
If only they had XOM to save them.
if only. Yeah.
Yeah, and one thing, since we've talked about the pthreads thread max value, they don't call out what the value is here in the post, so I'm not sure what the max amount is, or at least by default. I just want to make that explicit in case anybody's wondering what it is. You can probably look it up, but I don't have it offhand.
Yeah, it's kind of interesting. They don't talk about what that size is or what that max is, but they talk about the stack size being 2 MB by default.
Yeah, and the address. Like they
Yeah,
gave the
so
other
everything
constants,
else is
but not.
provided basically.
Yeah, I
I,
thought that
I, I
was a
guess
little bit off.
I guess I should say the fact that the stack size is 2 MB is worth calling out too, because that is a lot of space when you're talking about mappings, especially in 32-bit. So the fact that the stack size is that large means you probably don't need too many threads to run into this problem. But yeah, it's going to be somewhat specific on your target too. All right,
Feel
so
like for a stack size, like 2 MB feels like a pretty common-ish default.
yeah, that's true. But I did want to bring that up because it's like if the stack size was only like, let's say, 100 KB or 400 KB or something, it would be more difficult and less practical to exploit it potentially on some targets. But because it's 2 MB, that is occupying quite a bit of virtual address space, so it makes it a bit more possible to take advantage of, I guess.
Yeah.
All right, so we'll get into our next post here, which is a post by Maxwell Dullen on getting an AES key and hacking a scoreboard. So this is a 3-part blog series. Um, this is part 2, though part 3 is out now. I think it got put out yesterday. So yeah, part 1 covers some of the initial reverse engineering and information on the target, which is just like a scoreboard that he was looking at. Um, covers some like initial signal analysis, getting the modulation scheme and how you can extract bits from the packets within spectrum analysis. Then analyzing and reversing those packets by observing inputs versus outputs. But it ended up turning out that the packet payload was encrypted in AES 128, which is where this post comes into play, which deals with breaking that AES and getting the key.
Yeah,
Um,
and just as a quick comment on like the whole post series, good set of posts, kind of not so much on the binary exploitation. This is just low level hardware stuff for the most part, but really good set of posts on the whole process that he went through. He calls out, some of his failures here and all the things that didn't work, which again, with so many write-ups, that's missing. It's all like, here's how I successfully did X, while leaving out all of the steps that went into it. Leading to those imposter syndrome thoughts and everything else, where it's like they just knew everything. So I appreciate seeing a lot more of the background in this post, and he just includes a ton of details about the whole process. Very kind of background detail or background information heavy. Probably a good place to look if you're going to approach doing something kind of similar. There's a lot of good knowledge in here. Going kind of beyond, I don't do a lot of the hardware level work, but it seems like a really solid post in that.
Yeah, same here with respect to not doing a lot of hardware level work. I've always been saying that I'll get more into it, but then I never do. It's like when I say that I'm gonna pick up Rust and I never do, but whatever. Beside the point. So yeah, in the second post here, he goes through a little bit more of that hardware stuff, mapping out the PCB. The setup is a little interesting. They basically use a Raspberry Pi and also communicate with a microcontroller as well as an RF receiver, radio frequency for doing wireless stuff. And yeah, it seems that RF chip was kind of responsible for the encryption, but had to go through some RE to figure that out. Um, so yeah, he discovered that the RF chip would communicate with the microcontroller over SPI, over the serial peripheral interface for those that don't know what SPI is. And then the Raspberry Pi would receive that data from the MCU over serial and display it on HDMI. So when he was able to get more information on the packet structure, he was able to do that from the Raspberry Pi firmware, which was just loaded on an SD card inside the Pi. Wasn't really too much done to try to prevent somebody from getting that if they wanted to. And from that, he was able to figure out which fields in the payload were used for things like the shot clock, the game clock, and some of the other statistics that show up on the scoreboard. Unfortunately, he wasn't able to find the key on the Raspberry Pi firmware. Seems decryption was done in an earlier part of the pipeline, either in the MCU or the RF module. Turns out it was actually done in the RF module. And what he ended up doing to get the key was man in the middling the spy bus between the MCU and the RF module. Because it turned out that even though the RF module is performing the encryption, it loses its configuration on power loss. So it would need some, persistent store for the key. And that key was transferred over from the MCU over serial to the RF module. So by just sniffing the spy bus, he was able to extract the key, which he did with the Saley logic analyzer. And the best part of all this is it turned out that key was hex 1, hex 2, hex 3, hex 4, all the way to 8, and then repeating again. So, not exactly a very cryptographically strong key there, but it's just one of those things you can laugh at once you put in all the effort and do this complicated attack when meanwhile you could have brute forced it or guessed it or whatever. But
yeah, but brute
that wouldn't
force
have
is
been as
not.
fun.
Yeah, brute force is not an elegant solution. This is a much more cool solution.
For sure.
And
Yeah.
I mean, again, I'll say it again. I appreciate seeing the whole process that he went through for this, including the failures and the, he has a little bit about threat modeling, and just kind of coming up with some of the attacks, writing them down, and then looking at them, realizing they don't work until he eventually does get that one that works. And I will also mention the third post up here. So after this, he goes through and on the first post, he gets the AES key, got something, but they're still needing, and he has the packet format, but some of the data isn't quite right, and that's where he kind of gets into data whitening, and basically the whitening process there is just so the application is sending a long string of zeros or ones. Um, it'll do this whitening, which is basically XORing it with some random data in order to basically randomize the data so that it appears nicely. It goes through the whole process here of breaking the LSFR random generator. I'll try to say this. It reminds me a lot of, or I mean, it would be pretty much the same sort of attack as you would do against, say, breaking RAND and C, which I believe also will use just the linear feedback shift register. I think it's a fairly simple attack there. Nice thing here is this was only a period of like 511, I believe. He calls it out in here. So only 511 possible output or possible states for it to be, so a lot easier than some other situations, but still goes through the whole process there, breaks it down really well. So I won't dive into exactly how that went, but he does go into it in the post. Eventually, coming through there, gets the CRC, cyclic redundancy check, figures that out, goes through all of this, ultimately coming down to different attacks that he was able to, or could in theory perform, because once you're able, broken the encryption, can send your own packets over there, know the format, know where it is when it comes to the feedback, or the basically the random number generator, have that state broken. Once you have that, now it's just what can you actually do with this level of control. And he raises kind of the easy attacks, does raise replay, which honestly is one of those really fun sort of magical attacks when you're dealing with crypto stuff. Anything that gets encrypted using ECB mode, it's an option where you can kind of start crafting your own packets through block swapping. And it's a really fun and almost magic feeling attack when you're able to pull it off, when you're able to mess with crypto in that way. Unfortunately, in this case, wasn't able to do something useful just because of the complexity of the data inside of the blocks. It works a lot better when you have some sort of way of controlling a lot of data, so you can actually take control of an entire block. If you do want to play around actually with that sort of attack, crypto cookies, I think, is a challenge on 0x0539 that I wrote. Let's pull it up here. And it's basically that sort of AS attack. I guess I am kind of spoiling the attack there, but it was kind of meant just as a way to play around with that sort of attack. I find it really fun, so I was kind of happy to see it there, even though it didn't work out in this case. Had a horn denial of service, so could cause the scoreboard's horn to go off. Realize that. I believe they're sending on off repeatedly. That kind of seems to be the implication here by alternating horn on, horn off calls. They were turning off the audio system rapidly, leading to a resource exhaustion and denial of service that way. But earlier on, they say if one packet had horn on, one did not. So I'm not sure if this happens after just one, or if it is spamming it. I believe it's spamming because that seems to be how the rest of it goes. But then they get into the subtle attacks, which is what I thought was really kind of an interesting approach here, especially the fact that they could slow down the clock speed. They had the clock running. They used the example video here, clock running at just at a faster rate of 0.9 seconds per second, kind of stripping out a tenth of a second every second, which sounds just like a crazy attack because nobody's really going to notice that in real time, at least. That, in the last minute, they lost 6 seconds or something. Like, it's not super obvious, like a person there. So that just seems like a really cool attack to take on. And it goes over other control that they had, but this time one I think sounded like a really interesting attack.
I think the first time I've seen attack that would have impact on an like competitive integrity kind of thing. It's like very unique to this kind of target, and I hadn't even really thought of it, but yeah, I mean, if you were trying to sway a game or something, it could have a big impact.
Like, the thing that surprises me is the fact that that's something that can be, I don't know if it's configured or if it's kind of manipulated. Yeah, I would say like, maybe if you're getting high resource, you can have time running slower, but he does speed it up here. So it seems like it's configurable. And that just seems like a odd feature to even have in the first place. So I'm actually kind of curious now about what they do to cause that, but it is an interesting attack nonetheless that one could do this. And yeah, I mean, it would have, that competitive integrity aspect to the attack, as would a lot of these other ones. The possession arrow he calls out as like a lower level basketball thing, or a team foul count being able to modify some of the values there that might not get noticed if there's like a break in gameplay. And the other one is the intentional malfunction attack, just messing with the scoreboard, causing kind of a timeout without a team actually needing to use one of their timeouts.
Forcing a technical timeout, basically.
Yeah, exactly.
And this is definitely something that has been done, because when I saw this section, when Z pulled it up on the screen, I was thinking of the older CS days, because I do watch some professional Counter-Strike, and in the older CS days, people would literally, if they needed a timeout, they would just kick their PC to get it offline, and then be like, "Oh no, my PC's broken. I need a few minutes to fix it," and then they would strategize or whatever. So it's definitely like an attack that could happen.
Yeah, actually, Maxwell here does call out this was the first hack of a wireless scoreboard. So, I mean, at least for these wireless scoreboards, as the attack that you're talking about, that's totally something that could happen. As this, it does seem like at least first published research on it. I can't imagine too many people have really looked at scoreboards. And yeah, a great series of posts. A lot of cool information here. Some of it, I'll admit, I did skim over. I'm not that interested in the hardware hacking, but what I read seems solid, and I do love these attacks at the end.
And it's kind of funny because I was a bit the opposite. I found the hardware stuff more interesting, and especially the crypto stuff. And along those lines, going back towards the top of the third post, I will say when he talks about the data whitening and like the permutation on the bits that are going across, that's something that I wish there was a little bit more public resources on, because it seems to be somewhat common practice to have in place. And even if it's not necessarily intended to be like a security thing, it can throw off your efforts to like recover a key or something, or recover some kind of data if it's permutated. yeah, it's just not something that's really talked about very much. So seeing it talked about here was neat.
I think there
Because
is
yeah,
a good number of resources actually about breaking like linear feed shift registers, because that is just the classic way of implementing a random number generator. It's a very traditional technique they use here. Like I said, C did it. Either they still do it with rand, or they did it for a long time. Like that's basically how like the first RNGs would have been implemented. Um, and breaking it, like it's still common to see this sort of RNG everywhere. You wouldn't necessarily see it called as like the data whitening. It's just a random number generator, and you'll find information about breaking RNGs. Definitely on a lot of crypto resources, but elsewhere too. So I think
yeah,
that's
it's
more of a
probably
terminology thing.
yeah, it could be. Very well could be. But yeah, like you said, like it is a very good series of posts, and even though it deals in some of the hardware hacking and some of the stuff that Z and I don't really have a lot of experience in, it's very accessible. Even if you're not in that area, a lot of the like the PCB layouts and everything are all there. He breaks down step by step what he's doing and why he's doing it, and there's not too many crazy obstacles in the way, other than the encryption. So it's very accessible series of posts. So yeah, I enjoyed them a lot. All right. So unless you have anything else to add, Z, I guess we'll move into our shoutouts.
Nope, nothing else to add in there. I'll just take the first shout out here. I've got her. I think the only shout out for this episode, when Hypervisor met Snapshot fuzzing. I saw this. Um, we talked a little bit about covering it, but there isn't much of a vulnerability to cover here. It's just I think it was a wild copy, wild write. Yeah, wild copy. Vuln wasn't too interesting. There's some code in here, but it's basically, it seems like he's writing a fuzzer for Hypervisor, specifically VirtualBox, looking at SVGA. Some code in there. Worth checking out if that is an area of interest to you. Goes through their development of a fuzzing module for it. So I just wanted to give it that quick shout out. Check it out if that's of interest.
All right, cool. So that's everything that we have for this week. As always, thanks to everyone who tuned in. VOD will be up on YouTube and other platforms tomorrow. Links for everything and summaries can be found on our site at day0sec.com. Remember to follow our Twitter and join our Discord if you want to see notifications of when we're live and whatever other content we put out there goes up. And with that said, we'll see you all next week.